Right. Thanks. So I think a couple of weeks ago, we saw a presentation about learning from dynamics, which seemed to be about learning the linear dynamical systems from observations. Um, Kalman filter is kind of different in the sense that we assume the system is known, but we want to estimate the state. So, all right, so we start with linear dynamics. So this is just an ODE in Rn, where x is the state vector, u is a vector of forcings. So it's also the control vector, in other words. C, the matrix C, so y are the measurements, and C can be thought of as, the measurement matrix. So it kind of measures some things from the state. So for example, it could pull out the first component of the state, and that could be the measurement, for example. Okay, so A, B, and C are the system matrices which govern the dynamics and the measurements, and X, Y, and U are the variables. I've also added noise here, so WD and WN. All right, and I think what we had seen a couple of weeks back was the discrete time version, which looks essentially identical. It's just instead of the derivatives, it's time stepping forward. And again, there's the same noise terms in the system matrices. Okay, so so we start with motivating full state estimation. So this was our system. We assume A, B, and C are known. So that's not a problem we are worried about. And we impose some noise model. So here we are saying that WD and WN are white noise. I don't know why the rendering is a bit weird. It's not very high resolution either. Yeah. Anyways, so right, so these are white noise with variance matrices VD for the disturbance to the system and VN for the measurement noise. So this statement as written is formal. So technically the system of ODE should be SDEs, and then WT, the white noise can be interpreted as the derivative of the Brownian motion. So technically when you write it as as a SDE, that's going to be Brownian motion multiplied by a matrix, which gets it to the correct variance. But this notation can be quite convenient. Yeah, the delta is a direct. Yeah. So, right. So if we write it as dxt equals, a, basically using the SDE form, it's going to be in terms of Brownian motions instead of white noise, which should be quite similar. Yeah.
What's the distinction between disturbance and measurement?
So the disturbance is what's happening in the system. It could be so you have a physical system that's evolving. There could be some external sources of disturbances which mess it up, or it could just represent the uncertainty in our knowledge of the system. So if it's modeling a spacecraft, for example, the disturbance could be some meteor bits crashing into your spacecraft. Whereas measurement noise is the noise which we are measuring, and then our sensor is wrong, and the corruption in the sensor, for example. So they are kind of different, and then they need to be balanced somehow later. Okay, so the typical goal of a control system is to control it or stabilize it using the variables u. Okay, and typically we would like to do this using a closed loop feedback. So we would like to measure the system, and based on the measurements, we design the u such that the system is stabilized. So technically, the full state feedback would involve a term like this, where U is some gain matrix, things called the regulator matrix multiplied by the state. And in some sense, this is optimal, at least in linear systems. But the problem is that we don't always know X. So then what we would want to do is from possibly low dimensional measurements Y, we would want to estimate X and then feed that X, the X hat back into the feedback controller. All right. So typically Y can be really low dimensional. So it's not the compressed sensing setting, I guess, where M is low, the number of measurements is like equal to the intrinsic dimension or something. It can be just one measurement, just one coordinate, and in certain systems that can be sufficient to actually estimate the state. because we have knowledge of the dynamics as well. Okay, so in other words, so before I go into that, there's two sources of information based on what I just mentioned. So not only is it this, but also the dynamics. So we would want to leverage the information in the dynamics as well as the measurements to come up with an optimal estimate. And that's why it's different from the compressed sensing setting, which just like a point-wise, one shot measurement. Okay. Oh, this is really something's really off with the rendering. Okay, now it's good. It's odd. So to be able to actually estimate the state, we need to consider the observability matrix. It's defined like this. It's not sure what's going on. So this, you may recognize this from the lecture a couple of weeks ago, where this is in some sense a discrete time impulse response. But the rank of this matrix is what determines if state estimation is possible. So a system is defined to be observable if the observability matrix has full row rank. And a singular value decomposition can be used to kind of have a quantitative notion of this. So if the lowest singular values are sufficiently non-zero, that would be a quantitative notion. And then along with that, that gives you directions in your state space along which your system is more or less observable. One intuitive way to see why this matrix needs to be, full rank is by observing this. So suppose we have no noise and no control inputs, so that y can be represented as a function of the initial position like this by solving the differential equation. And suppose y0 equals c of x0, that's just at time t. So let's say that c is just a row vector, so y is just a single measurement. So of course, then we can't invert this equation. But we could take a bunch of derivatives if we have access to its history a little bit, and then its derivatives evaluated at 0 will turn out to be c, all the way to ca n minus 1. And now this is full rank, and so this can now be inverted. So that's like an intuitive way of seeing what's happening there. All right. One more thing observability lets you do, which I couldn't quite find a neat proof of it, though, is that if I write this matrix A minus KFC, where KF is some design matrix that we choose, by getting an appropriate choice, we can place the eigenvalues of this anywhere in the complex plane that we want. So I believe the proof of this kind of involves transforming the original state space system in an observable canonical form and then working with the eigenvalue equation, but couldn't quite find a neat, I couldn't quite understand that fully yet. So it was, I just kind of roughly saw that through such a transformation, you can kind of get at it. But if you can do this, then that means that you could kind of design a dynamical system within the physical dynamics that's happening, and then you can control how those dynamics behave, which is what the Kalman filtering scheme would do. So yeah, so we'll get to that now. So let's say the system is observable and we want state estimation. All right. So the filtering scheme should take in as inputs past values of the control input and measurements, which we have access to, and should output an estimate. So the estimation scheme is another dynamical system. So we can kind of run this dynamical system in parallel. It's a way of thinking about it. Or you could think of it as an input-output box, which takes in u and y and then outputs x based on solving this differential equation. So, right, so this is the estimate, and it satisfies this set of differential equations. So it looks almost identical to the original system, but there's no noise, and there's this additional term. So we can see that x hat evolves according to the original dynamics, but there's a correction term. So if the predicted dynamics based on this are different from the observed dynamics, you correct it. And Kf is still yet to be chosen, but you can write it this way. And once you have set this up, you can define the error vector to be the difference between the true state and the estimated state. And hopefully, if things go well, this error vector should converge to 0. All right, so wait, what happened here? Okay, that's not bad. It still works. So this was the, sorry, what do you call that? Yeah, this was the dynamical system we created. And then we can compute the derivative of the error and find the dynamical system that the errors satisfy. So if you differentiate it and plug in the true dynamics here and the filtering dynamics here, you would get a bunch of things would cancel out and you would get these terms. And so now we can see why the eigenvalues of this matrix were important. So in other words, if there were no noise terms, this would just be an ODE. And if all the eigenvalues of this were sufficiently, all the real parts of the eigenvalues of this were sufficiently negative, the error would decay really quickly to 0. So yeah, and then, so that would be ideal in the sense, ideal in an ODE sense if there was no noise. Now the problem is that when we do introduce the noise terms, there's this matrix multiplying the measurement noise, and if K kind of tries to attenuate the noiseless dynamics too strongly, it can blow up this noise, and that could be a problem. So I also had a few notes about this. So firstly, again, this is an SDE system because of this noise. So, we'd have to be a bit more careful in its analysis. It's not just an ODE. Secondly, yeah, this is just what I was saying, that if KF is too aggressive, it could blow up WN. And lastly, we need to find a balance by minimizing a cost, the balance between killing this term and not blowing this up. And that precise choice of KF is called a Kalman filter. So we can define a cost function, J, which is the long time limit of the squared error, the expected squared error under these noise terms. And this, under the hood, it depends on the covariance matrices of the measurement noise and the disturbance. So I tried to find a good way of computing this easily, but had some trouble looking for it. There were some other approaches to the Kalman filter as well, which kind of did things differently. But the one which I found intuitive, I didn't quite find a way of proving this. But they show that the minimizer of this can be written, so the KF, which minimizes this, can be written as some matrix Y times C transpose times the variance of the noise term, where Y is the solution to an algebraic Riccati equation. And that in particular depends on A, C, and B, and the noise variances as well. So solving this system can be order n cubed in the state dimension. And so that can take, it can be kind of bad for big systems, but for moderate systems, it's all right. So that's one thing. And another thing I wanted to mention was, yeah, I think I didn't write this down, but so going back to the controllability matrix. All right, so this is the controllability matrix. So another, sorry. Oh yeah, sorry, the observability matrix. Oh yeah, it's kind of like a transpose of this. So for the observability matrix, there's an equivalent condition to determine observability. And that is, if I write the matrix A minus lambda I and C. Okay, and this is, so the system is controllable if and only if the rank of this matrix Oops. The rank of this matrix equals n. That's full rank for every lambda in the complex plane. So first of all, this matrix is n by n, and it's going to be rank deficient only if lambda is an eigenvalue. So you only actually need to check for the eigenvalues of the matrix. And when we do that, at particular eigenvalues along the eigenspace, that's precisely the space in which this matrix is going to be rank deficient. So the matrix C has to complement this rank deficient matrix to fill up the rank. So you can, for simplicity, imagine that C is just a row vector and all the eigenvalues are distinct. So, in particular, then that all the eigenspaces are just one-dimensional. And so the condition for this observability would then be that the vector C has some non-zero component along all of the eigenspaces of this matrix. And so it can then be shown that if C is generated randomly, then with high probability that's going to happen. And so with high probability, things are going to be controlled. So yeah, I guess that's all I wanted to say. This went much quicker than last time. I think the written talk takes much longer than slides. So I'm sorry, I kind of misestimated how long it would take.
Yeah, in your last slide, I didn't get the noise covariance matrix.
Yeah, I didn't really show that. The end, right? So exactly how we get this, I'm a bit unclear on that, but why? That's because this x minus x hat, that's the error, right? And that's precisely this object, and this depends on WD and WN. So when I take the expected squared error of this, the covariances of both of them come into play. So the covariance of W.
But it also should depend on KF. Right?
Sorry, what you doing?
If you go back, that equation has KF in it as well.
Oh yeah, your KF is your optimization variable, and then the optimal point would be that.
How do you find this? If x minus x hat is the solution to that equation, how do you find it?
Yeah, I couldn't quite tell. So I think the resources I found were more aligned towards controllability, and then they used a dual argument to prove observability. So in controllability, what happened was we had this cost function. X transpose QX plus U transpose